Hello, today we are moving on to section 2 of chapter 4. So as I have mentioned earlier, last section, we are gonna talk about prime and composite numbers. So we are very familiar with prime numbers, I believe. What does that mean? Composite sounds like opposite of prime numbers, but what does that mean actually? So we are gonna talk about that today. All right, so let's think about the factors. So when you have a number such as 12, how can we make an area that makes 12? Well, if we have 1 by 12 squares, that makes 12 square units, whatever that unit is, right? That's not the only way to make 12 as an area. We can also have 2 by 6 or 6 by 2, or we can do 3 by 4 or 4 by 3. So all of these are the combinations that we can have to make 12 as the product. So we call that 1, 12, 2, 6, 3, and 4 as factors. Why do we talk about factors in prime numbers? Because the definition for prime numbers are coming from the factors. So if any whole number with exactly two distinct, which means two different whole number divisors or factors, is called prime numbers or a prime. For example, pick a number like 2. We can make only 1 by 2 or 2 by 1. So 1 and 2 are the only factors to make a product of 2. So 2 has only factors of two numbers, two distinct numbers, 1 and 2. So it is a prime. Another example of a prime, 3. How can we make 3? By multiplying some numbers, two numbers, 1 times 3, that's all, right? 1 times 3 or 3 times 1. So we have only two factors of 1 and 3 to make a product of 3. So it is again a prime number. Let's pick another number, 4. Well, 1 times 4 is 4, so we have two factors there, but are they the only two factors for 4? Not really, right? Because we can also have 2 times 2. So the factors 4 are 1, 2, and 4. How many are there? 3. There are more than 2 distinct factors to make 4. So we call that number 4 as a composite number. When you have any whole number greater than 1 that has a whole number factor other than 1 in itself is called a composite number. So when you have more than 2 factors, it is a composite number, just like 4. Let's go a little bit more. Let's think about 5. What are the factors for 5? 1 times 5, that's it, right? There are exactly 2 distinct whole number factors, so it is a prime. How about 6? 1 times 6 is 6, but that's not the only factors, right? There are also 2 times 3, so there are actually 1, 6, 2, and 3 as the factors of 6. So 6 is also a composite number. Let me ask you a question before I move on to the example. Let's consider 1. How about 1? Is 1 a prime or composite? Think about it. Okay, now 1 has a factor of what? Only 1. 1 times 1 makes 1, right? So there is actually only one factor. Does 1 have exactly 2 distinct factors? No, just one factor. So it is not a prime. Then let me ask you again. Then is 1 a composite number? No, because the composite number is supposed to have more than two factors. More than two factors. There's another factor other than 1 in itself, right? So 1 is a special number that is neither prime nor composite. Okay? Now, I want you to think about 2187. What do you think? 2187. Do you think 2187 is a prime number or composite number? Why? Once you are done, move on to 1331. Pause the video, figure it out, and then come back. Let's consider these two examples to figure out whether these are composite or prime numbers. So when you're thinking about how to find it out whether the given number is a prime or composite, you need to think about the factors of that number. So when you're thinking about that, I want you to start with a prime factor. Why do we start with a prime factor, not composite factor? Because think about it, composite number has already more than two factors. There are at least three factors there. That's what the composite mean, right? So if it is already divisible by a composite number that has already more than three factors, then this number will have more than that three factors. So you don't even have to think about dividing these numbers by composite numbers. So you're gonna divide the given number with only the prime number to figure out it is only factoring by the prime number. Okay, so if we are doing, because look at this, let me explain that a little bit more. So if it is only divisible by 1, no other prime numbers are dividing that. So 2187 is these two are the only factors. It is of course prime number, right? But if there are another number that makes, so let me go back. If there are another number, not only that, something like 3 times something is also 2187, then you have already 1, 2, 3, 4 factors, right? So we're just gonna figure out whether it is divisible by a prime number. Okay, always think about that. Always remember that. So let's see. So the first prime number we want to check it if it is divisible by 2. If you guys remember about the divisibility test that we talked about in the last section, then of course it is not, because the last digit, the ones digit, is not divisible by 2. It's not even number. So no, it's not divisible by 2. Let's consider 3 as the divisor. So does 3 divide 2187? What is the divisibility test for 3? Yes, very good. You need to think about the sum of each digit. So you're gonna add all of the digits together, and if that is divisible by 3, then that means actual number 2187 is divisible by 3. 3 divides 2187, right? But this is easier process. That's why we are going to do that. So here you can think about easy addition by using the comparable numbers. 2 plus 8 is 10, and 7 and 1 together is 8. So together that's 18. Thus 3 divide 18. Of course, right? 3 times 6 is 18. So if 3 divides the sum of each digit, then 3 also divides 2187. So we just found that out. This is divisible by not only 1 and 2187, those are the factors, but also it is divisible by 3 and something, whatever that is. You don't even have to find that out because we know that it is divisible by 3. So there is a certain number that makes a factor for 2187. So we can see that there are at least 4 factors. So it is a composite number. You don't have to go even further, because if it's a composite number, there should be more than 2 factors, and we already found 4. So you don't even have to look further, right? So yes, it is a composite number. Now I want you to think about 1331. So start from prime number 2. Does 2 divide 1331? No, it doesn't, because last digit here is not an even number, so it doesn't divide. How about 3? Does 3 divide 1331? So let's consider the sum of the digits. And I see 4 and 4, 8. That is the same as 8, right? 3 does not divide 8, so 3 is not the factor. We don't have to check with 4, but we can move on to 5. Does 5 divide 1331? The divisibility test for 5, we just need to look at the last digit. If it ends with 0 or 5, it is divisible by 5, but obviously not. So nope, it's not divisible by 5. How about next prime number, 7? What's the divisibility test for 7? Oh, we didn't even talk about that. So you can just actually divide that by 7. Then 1331 divided by 7. One number goes into 1. No, nothing. So let's look at the second digit, 2 digits. 7 times 2 is 14, which is too big. So 7 times 1 is 7. Subtract and you get 600. And you can drop that 3 down. We have a 63. So 7 times 9 is 63. So we have subtraction there and got 0 and drop that 1. There's 1. That's way too small for 7. So we know that the quotient is not 19, but it's 100, 90, and nothing here in the ones. So 190 is the quotient, and there's a remainder 1. If there's remainder other than 0, that means it's not divisible by 7. So no, it's not divisible by 7. What's the next number? Next prime number? Not 9, because 9 has 3 as another factor. So next one is, yes, 11. Does anybody remember divisibility test of 11? There we go. So we're gonna add every other number, right? And we find the difference between those two sums. So 1 and 3 together is 4, and the other sum, the other digits sum is 4. So 4 minus 4 is 0. 4 minus 4 is equal to 0. Does 11 divide 0? That was the good question that I asked you, right? And yes, it is. Any number divides 0. Any number divides 0. So 0 divided by 11 is always 0. 0 divided by any number is 0. But if your denominator is equal to 0, it doesn't work. It's undefined, right? Okay, so 11 divided by 0, yes. That means this has 11 as a factor other than 1 and itself. So it has more than 2 factors, which means it is not prime, it's also a composite, right? Because it has more than 2 factors. Let me actually give you more examples. So let me see what examples we have. Okay, so in the next slide, if you see the class notes, I have more examples there, and I will just write it down here. So that's example 9. We need to show the following numbers are composite. So first one is 1564. Second one, 2781. Third one, C, 1001. B, 3 times 5 times 7 times 11 times 13 plus 1. You're gonna consider all these numbers together. I mean all of them, whether they are composite or not. So pause the video again, okay, and then come back when you solve them. So did you have some time for that? So let's think about 1564. You see that the divisibility test of 2 already tells us it is also divisible by 2. So there are not only 1 in itself, but 2 is another factor. At least there should be more, right? So it is composite. Okay. How about 2781? It's not divisible by 2. Let's think about 3. So to find out the divisibility of 3, we can just add all the digits together and see if it is divisible by 3. So when we are doing that, I see 2 and 8 is 10, and 7 and 1 is 8. So we already know that 3 divided by, that's same as 3 divided by 18. Yes, it is divisible, so it is composite number. Because 2781 not only has 1 in itself, but also 3 as a factor. How about 1001? 2, does 2 divide 1001? No, it doesn't, because it's an even number. Nope. So how about 3? Let's add them together, and 1 plus 0 plus 0 plus 1 is 2. So no, it's not divisible. Next prime, 5. No, it's not. It doesn't end with a 0 or 5. So 5 doesn't divide 1001. How about 7? Does 7 divide 1001? So if you divide that by 7, you get 7 times 1 is 7. Subtract and you get 3. And the next digit is 30. So close one is 28. No. 4 times 7, 28. And subtract, you get 21 and 3. So that's 21, and the remainder is 0. So 7 times 143 are the another factors other than 1 in itself. So it is divisible by 7, right? So we can say that, yes, it is also composite number. And I also see that this is divisible by 11, because every other number, these two, sum of those two is 1, the other two is 1, the difference is 0, then it is divisible by 11, right? So it's also divisible by 11. So whichever comes to you, you can do that. Okay, anyway, it is a composite number. Now, this is a question that I'm asking you to consider even harder. Okay, so if we don't have plus 1 here, if we don't have plus 1 here, we know that this number will be composite number, right? Because you see, 3 is a factor, 5 is a factor, 7 is a factor, 11 is a factor, 13 is a factor. You know, combination of any numbers are all the factors for whatever that product is. But if we add the number by 1, what happens? Then it becomes prime number, because there is no other number that goes into both terms other than 1, right? There's no common factors between this term and that term other than 1. That means there are only 2 factors, 1 and whatever the product is. This whole number, when you multiply and add by 1, those 2 are the only factors. So it is a prime number. Okay? Alright. Now let's move on to, so we just finished this one. Okay. Let's talk about fundamental theorem arithmetic. So fundamental theorem of arithmetic is each composite number can be written as a product of primes in one and only one way, except for the order of the prime factors in the product. Which means if you are using only the prime numbers as the factors, then there's the only way to show that. Okay, so we're gonna have some practice for that. So to do the prime factorization, my favorite way is using factor tree, such as this. Okay, I see the branches here, and 200, these, I will explain what that means. So when you're thinking about 260, using the prime numbers as the factor. First smallest prime is 2. And does 2 divide 260? Yes. 2 times what makes 260? 2 times 130 makes 260. So I will circle this. In this example, it just showed a different color. So the green colors are all the prime factors of 260. Okay, and the blue colors, you have to keep going on and on and on until you cannot do any further because you have all the prime numbers, prime factors out. Okay, so first thing you can do with 2, and 2 times 1 makes 260, 130 does. 130 is not a prime number, so keep going. 2 times 1 makes 130, 2 times 65 does. 2 is a prime, 65 is not. So continue. So, but we are done with the 2, so move on to 3. No, it doesn't work, but it is divisible by 5. So 5 times 1 makes 65, 13 does. And hey, 5 and 13 both are the prime numbers. So we can go any further for prime factorization because it's prime number already. So there is no other factor other than 1 itself, right? So we have factors of 2, 2, 5, 13. So how do we write this? We can say 260 is equal to 2 times 5 times 13. Or we can simplify that as 2 squared times 5 times 13. If we use a factor tree, it is like this. If we are using division of numbers here, we can just count these numbers as factors, prime factors. So use only prime numbers here to divide 260. So divide 260 by 2, what do you get? 130. 130 divided by 2, what do you get? 65. Only the quotients come here. And 65 is divisible by 5. 5 times what makes 65? 5 times 13 makes 65. And 13 times 1. So these are the only prime factors, right? If we rewrite that, it's the same thing. 2 times 2 times 5 times 13. 2 times 2 times 5 times 13. Isn't it? So we have 2 times 2 is 2 squared times 5 times 13. Okay? So there's no other way to show 260 when you are using only the prime numbers as factors. So that is fundamental theorem of arithmetic. Okay? This theorem that we're going to talk about is theorem 413. You don't have to remember the number of theorems, okay? But you just need to understand what's going on there. So this theorem here is talking about if D is a divisor of a number n, where n is not 0, then n divided by D is also a divisor of n. That's so obvious, isn't it? Because, look, n is divisible by D. So, for example, 6 is divisible by 2. Then what's 6 divided by 2? That's 3. So 3 is also divisor of 6. Because 2 times 3 is 6, right? So if I just rewrite this part using my Jamboard, it's like this. So here is a composite number n. It is divisible by d. And there's a number q then, right? So we know the relationship here. So n is d times q. Thus, d is a factor of n and also q is a factor of n. That's what it means. Okay? So the next thing that we want to talk about is then, can we figure out the number of divisor? So I want you to think about this specific number, 24, as an example. Okay, I already have finished the prime factorization of 24. 24 is 2 cubed times 3. So 2 cubed is 8, 8 times 3. But 8 and 3 are the only factors for 24? Not really, right? 2 is also factor of 24. 4 is also factor of 24. What else? 6 is also factor of 24. What else? 12 is also factor of 24. And also 24 is a factor of 24. So is there any efficient way that we can find it out? That's my question. Okay, so I want you to consider that, but here are some, explanation about the divisor of 2 cube or 3, or or all of these numbers that we have as divisors. So think about divisors of 2 cube. If 2 cube is divisor of 24, the number that divides 2 cubes are also a factor of 24, because you can further factor that out with other numbers such as 1, 2, 4, and 8. So for 2 cube, we found 1, 2, 3, 4. Okay, I want you to pay attention to the number changing number. I said 2 cube has 4. So relationship between 3 and 4 factors. And think about divisor of 3 to the 1 power. I have 2 factors, 1 and 3. When you have 3 to the 1 power, you have 2 factors. When you have a 2 cube power, you have 1, 2, 3, 4 factors, right? And then you're gonna think about actual number, divisor of 3 times 2 cube or 2 cube times 3. You can just combine these numbers, in different combinations. So with 2 to the 0 power, which is 1, 1, with 1 times what makes 24? 1 times 24 makes 24. 2 times 1 makes 24. 2 times 12 makes 24. 4 times 1 makes 24. 4 times 6 makes 24. 8 times 1 makes 24. 8 times 3 does. How about with 1? 1 times 24, we already had done that. And 3 times we have done that, right? So we can see that divisor of 3 to the 1's power times 2 to the 3rd power, we can think about all of these by just multiplying number of 4 here, 4 factors times number of factors of 3, which are 2. So that's the only number of divisor for 24. So what did you find as the relationship between the powers of the prime factors and number of factors of this whole number? We found there are 4 factors for this part, and we found 2 factors for this part. And we see the relationship of 4 factors for this, which is 1 more than that exponent. And 2 factors is 1 more than the exponent of 3 to the 1 power. The total divisor of this whole number 24 was 4 times 2. So 3 plus 1 times 1 plus 1. Always just 1 more than the exponent. Multiply those two together, then you can find that out. Number of divisors of that certain number. So here is next theorem. If P and Q are different primes and N and M are whole numbers, then P to the N's power, Q to the M's power is the only way to represent the prime factorization of certain number. Then the number of divisors for that number is n plus 1, just 1 more than the exponent of the prime factor, and 1 plus the other one's exponent, and then multiply those together. If that generalization is a little bit hard, we can always practice with some examples. Okay, so let me use my Jamboard again and bring down that question example. So this is example 10. Okay, A is 1 million, B is 210 to the 10. The question is, find the number of whole number divisors. Whole number divisors. there should be a lot, right? So we're not gonna just find all of the divisors and say, oh, there are like 50 divisors. It takes so much time. It's a tedious job. So we know the more efficient way, right? If we do first, find the prime factorization, right? Find the prime factorization. Okay. So if we have something like 1 million is equal to A times B times C with M power M N Q, something like that, then 2 number of divisors is M plus 1, only the exponent by 1, just add it by 1, and the next exponent of another prime's exponent plus 1 and Q plus 1. You just multiply them together. That shows number of divisor. Okay? So remember this procedure. That's the shortcut to find number of the divisor of any of the numbers. So let's try with 1 million. 1 million. I see that 1 million, one more zero, has 10 to the what power? 1, 2, 3, 4, 5, 6 power, 10 to the 6 power, right? But 10 is not the prime number because 10 is divisible by 2 and 5. So actually 2 times 5 makes 10, but 2 and 5 are both prime numbers. So if you think about the prime, the exponent rule, we can distribute 6 to each of the prime numbers. To the factors is 2 to the 6 power times 5 to the 6 power. This is the only unique way of prime factorization for 1 million, right? Now we have a form of this prime factorization. Then number of divisors for 1 million, number of divisors for 1 million is 6 plus 1 times another 6 plus 1. So that's 7 times 7. So actually there are 49 many divisors. 49 factors are in 1 million. So obviously you didn't want to list all that and count them because there are way too many, right? How about 210 to the 10th power? If we factor using prime factorization 210, we can do that to the 10th power here, right? So let's figure out 210 prime factorization. I will use tree diagram. 210 is 21 times 10. The order doesn't matter, okay? You just keep going on and on and on with the tree branches until you don't have any more prime numbers to break them, okay? So 21 is not a prime number, and I know 3 and 7 are the factors. Whenever I see the prime factors, I will circle them. So I will count them in the divisor there. 10 is 2 times 5. So we are done. We only have prime numbers here. I will write them in order, increasing order, starting from 2. I have 2, I have 3, I have 5, and I have 7. So 210 is 2 times 3 times 5 times 7. Because of the commutative property for multiplication, the order doesn't matter in the multiplication. That's why we are just writing in the ascending or descending order. Okay, so that gives us more organized feeling. So I think that really helps. This is the same as 2 to the 10th power times 3 to the 10th power times 5 to the 10th power times 7 to the 10th power, because everything is 10th powered, right? Now we can figure out number of divisors. How? Number of divisors can be calculated as exponent plus 1 times exponent plus 1 times exponent plus 1 times exponent plus 1. So we have a 10 plus 1 times 10 plus 1 times 10 plus 1 times another 10 plus 1. And we actually have 11 times 11 times 11 times 11, which is 11 to the fourth power. So if you use a calculator, what does this say? 11 to the fourth power is 14,641. What's the unit? 14,641 divisors. There are 14,641 divisors for 210 to the 10th power, which is really many, right? So you don't wanna list all of that to find it out, but we know the more efficient way now. Okay, so that's how you find the number of divisors or number of factors. Divisors are the same as factors. Okay, and let's move on to the next theorem. Okay, theorem 415 is saying if n is a composite number, then n has a prime factor p such that p squared is less than or equal to n. This is very powerful too, because whenever you are testing whether the number is composite or prime, you don't have to check every number that is less than that given number, but we can just think about what's squared, so square root of that number only up to that point. Okay, so I will talk about that with sieve of Eratosthenes. I'm gonna show you a video, but it shows why we are thinking about p squared rather than just n. Okay. Next theorem is if n is a whole number greater than 1 and n is not divisible by any prime number, p such that p squared is less than or n, then n is a prime. So these two theorems are very closely related with sieve of Eratosthenes. So I will show you this video from Khan Academy. So let's watch this together. Hold on. Can I hear it? Right. Here we go.
I'm now going to introduce an ancient method for generating a list of primes up to some limit n, called the sieve of Eratosthenes. Now, Eratosthenes was born in 276 BC. So this method, is over 2,200 years old, but it's very simple and elegant, and you could teach it to any child. Now, let's say, for example, we want to calculate all the primes up to 100, but this would work in the same way if we wanted to calculate up to 10,000 or a billion. It proceeds as follows. Assume all numbers are unmarked. Gray is unmarked. We start at the beginning, and if we find a number that is unmarked, we know it's prime. So we hit 2, and we say 2 is prime because it's unmarked. And then the second phase is, now we can eliminate all multiples of 2 because we know they're composite. So bam, we jump along and we eliminate all multiples of 2. Red means composite. And now we repeat. We step along from 2 to 3. 3 is unmarked, so we mark 3 as prime. And now we can eliminate all multiples of 3. And a really simple optimization is, notice 6 is already crossed off. We actually cross off the multiples starting at the square of that number. So 3 times 3 is 9. We start at 9 and mark all multiples of 3 as composite. And again, we go back, we jump along to 4. Well, 4 is marked, we know it's composite. Then we jump along to 5. We found an unmarked number. 5 is prime. Now 5 times 5 is 25. We go to 25, we mark off 25, 30, 35, 40, 45, and so on. Those are composites. We proceed forward until we hit 7. We know 7 is prime because it's unmarked. 7 times 7 is 49. We mark 49 and all multiples of 7 above it as composite. And now we move along until we hit 11. 11 is prime. And notice now, 11 times 11 is greater than 100, so we can actually stop at this point. We could have stopped at 10 even, because now all remaining unmarked numbers, if you'll notice, are prime. And we could, in one swoop, mark them all as prime. And that's the whole algorithm. It's so simple. And just to generalize how we do this, so we could write up a program to perform this sieve, is if we want to find all primes up to some number n, we first create a main loop. So we have for all numbers a from 2 to the square root of n. So notice here we stopped. When we hit 10, or if I showed it as 11, we actually stop because we have found all primes. So from 2 to the square root of n, we proceed as follows. If a is unmarked, then we know a is prime. And when we find a prime number, we mark all multiples of a off as composite. And that's it. So you find a number prime, mark off the multiples, go back to the beginning, increment a by 1. So we're on 2, then we go to 3, then we go to 4, 5, and so on. And when we're done, we have all primes. Notice here that this is also a loop. So we have a main loop for, and when we find a prime, this marking off of multiples is also a loop. So it's important to notice here that we have a nested loop. We have a loop inside a loop. Here is an example of this algorithm in action. I wrote in JavaScript below. If I put in 100, here are all the primes under 100. And if I put in 200, here are all the primes under 200. And if I put in 850, here are all the primes under 850. And below I have this program with a recording explaining how I set it up.
Okay, so that is a sieve of Eratosthenes. And yeah, so what we need to do is we just check only the square root of that given number, only the number that is less than square root of that number. And if you can find any prime number there, that is a factor of 397, then it is a composite number. If there's no prime number that divides square root of 397 or less than that number, then it is a prime number. So I will show you how to do that for these two examples in here Jamboard, and that's the last lesson for today. Okay, so let's check 397 first. In order to find any prime number factor for 397, instead of you just check every number for that, what we're gonna do, the most efficient way is find square root of 397. Find that first. So let's do square root of 397, and I have 19.9 number. So what we're gonna check is only the whole numbers up to 19.9. What are the whole number primes up to that number? 2, 3, 5, 7, 9, 11, 13, 17, and 19. These are the only prime numbers that are less than or equal to 19.9, right? So we're just gonna check whether 397 is divisible by any of these numbers. Divisible by 2? No, because it's not an even number. How about divisibility by 3? 3 plus 9 plus 7, 19 is not divisible by 3. Divisibility of 5 doesn't end with 0 or 5, so no. How about divisibility of 7? 397 divided by 7, it's not divisible by that. And 9 is not an even prime number, so you don't check it. I'm sorry about that. Divisibility of 11, you check every other number. 10 and 9, 10 minus 9 is just 1. It's not divisible by 11. How about by 13? Is it divisible by 13? So you just do 397 divided by 13, and you get 30.53 . So no, it's not divisible by 13. How about 397 divided by 17? It's not also divisible by 17 because there are remainder. How about 397 divided by 19? you get 20.8 dot 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 dot. So it is not also divisible by 19. What does that tell us? There is no number that divides 397, which means there are only two numbers of factors for 397, which means it is a prime. Okay, let me give you another example. 91. Let's think about whether 91 is a prime or not. So the most efficient way is, so I will say, I'm gonna put 1 because it's a procedure. You're gonna do square root of 91. If you don't have a calculator, you can also think about, well, 91 is, well, if we do 10 times 10, that's 100. 9 times 9 is 81, right? So that 91 is in between 9 and 10. So that will be something like 9 point something something something, even if I don't know, because 91 is in between 81 and 100, right? So 91 is greater than 81 but less than 100, and 81 is 9 squared, and 10 squared is 100, so in between 91. So we can do square root of 91 should be also in between 9 and 10, right? That's how I get square root of 91 is about 9 point something something something. So the only prime numbers, the second thing, you're gonna think about what prime numbers you need to check as a factor of 91. So 2, 3, 5, 7. These four numbers are only prime numbers less than or equal to 9 point something, right? So you're just gonna check of divisibility of these numbers. So now 3, check all of the divisibility. Does 2 divide 91? No, it doesn't. Does 3 divide 91? No, it doesn't. Does 5 divide 91? No, it doesn't. Does 7 divide 91? Actually it does, doesn't it? 91 divided by 7. 7 times 1 is 7. Subtract, you get 21. 3 times 7 is 21, equal to 0. So yes, it is divisible by 7. So we can say that 7 is divisible by 91 is divisible by 7 times 13. So 91's factors are not only 1 and 91, but there are also 2 and 13, right? So it is a composite number. Okay, so the sieve of Eratosthenes is start with square root of that number, and then only list the prime factors that are less than or equal to that square root number, and check the divisibility of that. If there's no prime number less than or equal to square root of that number is a factor, then you can say, oh, this number is prime. If you find any divisor of that the number that is less than square root of that number, then it becomes a composite number. Okay, so that's very powerful, and I want you guys to understand that. And that's all for 4.2, and I will see you guys next time. Okay, bye.